Okay, as you see, this discussion is about how we're going to analyze the graph of a function by using the derivative. Now, that's really broad. We're going to do this for several discussions, and what we're doing in this particular discussion is how we use the first derivative to find the values of x for which the graph of a function is increasing and the values of x for which the function is decreasing, or the graph of the function is decreasing. Now, a couple of things, as I just mentioned. We're going to use the derivative to do several things over the next couple of lessons. But in this lesson, it's specifically about finding where the function increases and decreases. And notice also I said how we use the first derivative. That implies that there may be something called the second derivative, and a little later we'll see that there actually is. But for now, we're just worried about the normal derivative that we're familiar with. Now, we start out by looking at examples of graphs of functions, and this isn't so challenging to make the decision about where this function is increasing or where it is decreasing. But we need to understand what we mean, and then we'll expand or go further with the idea. I say I've got a straight point on this graph, but let me right now point out that this vertex of this graph is really supposed to be 1, -4. And it's a little bit hard to tell because it looks like it's not quite lined up. I did this by hand, and of course it's not completely perfect. Now, what we have to be worried about when we see a graph, because it's normal we see on a graph that we have arrowheads. See, here's an arrowhead at the end of the graph, and here's an arrowhead over here at the end of the graph, and those arrowheads are telling us basically the graph is continuing in that manner. That's all that tells us. But when we want to know whether we're increasing or decreasing, we don't look at the direction of the arrow on the graph. We read graphs. This is important. We read graphs from left to right. Okay, understand that. We read graphs from left to right. So here is the idea. If we were a little bug, if we were a little bug here on this graph, say we were right here, and we were trying to move to our right. We were trying to go right, left to right. We're trying to move right. We couldn't walk quite right across. We would have to start going down this direction, wouldn't we? We'd have to go down, 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 down. So this little bug is going to have to walk down to go to the right. And so if that's the case, what we say here is that the graph is decreasing because the bug is walking down. So we're decreasing in this portion. Now, this bug is going to continue going down, 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 and then it's going to bottom out. Now, when the bug gets over to here, the bug is walking uphill, isn't it? Over here, the bug is walking uphill. Okay, so in this case, we would say that the function is increasing. Okay, so over here, we are increasing. So pictorially, we see the idea. We're ignoring the arrowheads here, and we're thinking about being on the graph and trying to move right. Now, once we see that, then, what we're really interested in is for what x values. We see where the graph is going down and where the graph is going up, but what x values are represented there. And so you see that we stopped going down when we reached this position, didn't we? And that position is associated with the x value of 1. See, that's where the x value of 1 is. So for all of the x values that are less than 1 out here, that is where the graph was decreasing. See, it's for these x values that the graph is decreasing. So we come over here and say, okay, the intervals for which the graph is in, the interval, we're referring to the x's, the interval for which the graph is decreasing is the interval from negative infinity up to 1. And although I've made my arrow go to the left, the whole point is it's all the values left of 1 are the x values for which the graph is decreasing. Now, on the other hand, when we get past 1, that is, when we start getting our x's that are past 1, then we're talking about these x's, that's when the graph is going up, isn't it? So the interval, remember we're referring to what x values, the interval for which the graph is increasing is from 1 to the right forever, and so we say from 1 to infinity. Now notice around the 1, I didn't include 1, because the issue is on the left side of 1, we're going down, and the right side of 1, we're going up. Left, we're going down, right, we're going up. At 1, we're doing neither, are we? We're not going up or down. And so 1 is not included in this discussion. That's actually the breaking point, the critical point for which we change from going up to going down. Now, what I'd like to do is continue this with a few more rougher sketches to talk about things that, well, here we go. We're going to have several graphs here. And I'm just going to rough them in, and I'm not even going to tell you what the function is. So, I mean, the formula for the function. So suppose we have a function whose graph looks something like this. And let's suppose maybe, I'm just doing this on the sly here, on the cuff real quickly. So here's 1, and here's 2, and here's 3. And suppose we had a graph that came in here and did something like this. It goes like this. Actually, you can even see as I'm drawing it, okay, you can kind of understand as I'm going through this drawing, then you can almost answer when I'm drawing up and when I'm drawing down, because usually that's what we do, is we draw from the left to the right, don't we? Now, I put arrowheads on the end, okay, but those arrowheads are just indicating that the graph is continuing to go in the direction that is indicated. But here we see that at this position, and that's supposed to match up with 1, and we see at this position right here, and that's supposed to match up with 3, we actually had a change in direction, didn't we? And so in here, although the arrowhead, in this position over here, although the arrowhead is pointing down, we're really thinking about walking left to right, and we'd have to walk uphill, wouldn't we? So here we're actually increasing. Okay? And then when we get up to the top of the hill, then we start walking downhill, don't we? And so now we're decreasing. And then we get to the bottom of the hill, and when we get to the bottom of the hill, then we turn around and start walking uphill again, and so we're back to increasing. So in this case, the function is decreasing only on one interval of x values, isn't it? It's decreasing on the interval. Let's see, where is that? We started decreasing when x was 1, and we stopped decreasing when started increasing again when x is 3. So in this interval right here is when we're decreasing the x values. So we're decreasing from 1 to 3. Now, on the other hand, it's increasing in 2 different intervals. Before we ever get to the x value of 1, that is, for the x values that are less than 1, that's this part of the graph, isn't it? It's this part right here, okay? And on that part of the graph, those are the x values for less than 1, so it's increasing from, from negative infinity. Okay, I've really bungled this. I'll start over. It's increasing from negative infinity up to 1, all from the left of 1. And then it starts decreasing, and then after we get to 3, then the graph starts going up again. So it's also increasing from 3 to positive infinity. Now, I want to do a couple more graphs on the next page to continue this thought because we'll have different looks. Okay, you can see on this page we have a new graph, and I just happen to tell you that it's the graph of, you see, x minus 2 to the power 2/3, or at least a representation of it. Of course, we have a point here instead of being nice and rounded at the edges. And again, we want to know where this function is increasing and where this function is decreasing, or vice versa. Now, this time I'm having to write increase first, okay? And then we'll consider decreasing, or vice versa. We'll actually kind of find out both at the same time. We're talking about intervals of x values. Now, we ignore the arrowheads that are on the graph, and once again, we think about a bug on the graph walking to the right. And of course, we start out over here, and if we're on the graph over here, then to walk right, we have to walk down. And so we would say it's decreasing on this portion of the graph. And then we look over, after we get down to the x-axis at that point, that's on the x-axis, then all of a sudden we have to take a quick abrupt change, and we start increasing over here, don't we? That is, we're walking up. We were walking down, and now we're walking up when we're over here. So we're increasing from 2 to infinity. We're decreasing from negative infinity to 2. Okay, here's another look. Suppose we have a graph that looks like, well, let's mix this one up a little bit. Suppose this is where negative 1 is, and here's where negative 2 is, and here's where negative 3 is, and here's where positive 1 is. Whoops, not too good there, is it? Yeah, I'm going to draw this graph. Okay, something like this. So the graph I'm drawing well, it's not a very pretty picture, but I guess that's not a big deal. Okay, this is supposed to represent the graph that we would get if we took f of x as 1 over x plus 1 in parentheses squared. It would look something like this. Now, again, we have to disregard the arrowheads that are on the graph. And we're going to answer the question once again, for what interval of x values is the function increasing, and for what values is it decreasing? I got ahead of myself, didn't I? Well, notice, of course, when we're on this part of the graph right here, if we walk to the right, we're forced to walk up. So that tells us that we're increasing here, doesn't it? And then if we're on this part of the graph over here, and we're trying to walk right, then we're forced to walk downward, aren't we? So we're decreasing here. Now that we have that idea, we see that we're increasing from negative infinity to negative 1, and then after we pass negative 1 for our x values, forever to the right, we're in a decreasing mode. So those would be the intervals of increasing and decreasing. And of course, we could have a very complicated function that went up and down a lot. I mean, we could have something that maybe started out like this, and then it goes like here, and all of a sudden it's doing this, and now it's going like this. There's all kinds of things happening. So there's a lot of different things we worry about. Let's suppose this bottom out point, let's suppose that's at A. And let's suppose this point that's up here, let's suppose that's at some x value B. And then we've got a bottom out point here, suppose that's at C. And then we have another point here that's kind of that peak point, and that's where x is B, okay? And so if we're talking about where this is increasing and where this is decreasing, we're going to have several intervals of each. Okay? Maybe make some room here. In fact, I'm just going to think from left to right now. So here we're having to go down, aren't we? So here we're going down. So it's decreasing from negative infinity to the number a. Okay, now once we get to where x is a and past a, we're on this part of the graph, and so we're increasing. So we're increasing from a, and we continue to increase until we get to the corner point up here, and that's where x is b. Now once we get to this point here and we continue to walk, we have to go down. So once again, we're decreasing now. And so when we're, in fact, we keep decreasing until we get to the bottom of this valley, don't we? And the bottom of that valley is at C, so it stops decreasing when we get to C. It starts increasing, let's put a comma to separate these intervals. It starts decreasing when we get to B, and it stops decreasing when we get to C. And likewise, after we pass C, we're increasing, aren't we? And we continue to increase until we get to this peak. So we started increasing at C, and we stopped decreasing at D. So we're increasing from C to D. And likewise, once we get to the x value D, we get past this peak, then we start to decrease again, don't we? And after that, we're continuing to decrease. So we'll decrease here then, and I'm afraid I'm going to run out of room. Well, let's just do it. We'll decrease here then from what? D, and continue forever decreasing after that, so from D to infinity. So we can have a whole lot of different things happen, and we just need to be prepared for each of those. Now we'll start, I'm going to pause here, and when we start back up on the next page, we'll begin to put together pieces so we understand how we can tell, not by looking at the graph, but by analyzing the equation or the formula for the function, just looking at the function and deciding how we can make the decision that it's increasing or decreasing somewhere. Well, as we continue this discussion of intervals for which a function is increasing or decreasing, we turn our attention to the tangent line. And this is going to help us make the decision analytically whether a function is increasing or decreasing. That is, be able to take the function itself without its graph and decide where a function is increasing or decreasing. So, as it's stated here, the slope of a tangent line as it relates to whether a function is increasing or decreasing. So let's draw a graph real quickly here. I'm not worried about having a perfect graph. Just something that we can quite deal with. So we'll start out with something fairly simple, just like maybe a parabola. Now, we understand, let's look at this position. See, the function is decreasing over here, isn't it? Decreasing. And let's imagine a tangent line that's over here. For instance, at this point, in this position, let's imagine the tangent line. So I'll just sketch something in here. That's what the tangent line would look like, isn't it? Now, that tangent line, because it's going down, that tangent line has a slope that is negative, doesn't it? The slope is negative. It's a negative number. In fact, if you can imagine any tangent line where the function is. Now remember, we'll just say this is A. So we understand that the all in this position over here, well, you can't see me point, can you? This part of the graph, we're decreasing in all that part of the graph. Okay, that's where it's decreasing. And any tangent line that we draw on this part of the graph is going to have a negative slope. So there's another tangent line. That's kind of hard to read, isn't it? Now, on the other hand, let me kind of get this over here so it's not quite as hard to see. If we were looking at this graph, of course, we would recognize that here we're increasing. Here we're increasing. And when we imagine a tangent line to this graph, for instance, the tangent line at this point, well, if we draw that tangent line has a positive slope. So we have a positive slope here. We draw another tangent line where it's increasing. That tangent line has a positive slope. And it doesn't take very much convincing to understand that when the graph is decreasing, that is, when the function is decreasing or the graph is decreasing, going down, the slopes of tangent lines are negative. Now, if the function, let's assume the function name, the function is f of x as an example. Okay. Well, the way we calculate slopes of tangent lines is by looking at the derivative, isn't it? Say, the derivative of the function. And so what we're saying is the slopes of tangent lines are negative. That would mean f prime of x is less than 0. That's what we would mean when we say the slope is negative. That's what it says. Slope is negative. Now, in a very similar fashion, when the graph, of course, and you're already seeing through this, when the graph is increasing, then of course the tangent lines are going up. When the graph is increasing, the tangent lines are going up. So we could say the slopes of tangent lines, since the tangent lines are going up, the slopes are positive. Well, if the slope is positive, say if the slope is positive, and the slope is nothing more than the derivative, that's the way we calculate the slope, we're talking about positive derivatives. And this really sums everything up right here. This is the big deal. So let me summarize it in this fashion, and then we'll see how this works for us more in the future. But this is the important thing. The function f is decreasing when the derivative is less than 0. That's when the function is decreasing. Also, the function f is increasing wherever, actually wherever is what I should be saying, but I'm going to say when the derivative is positive. Remember, derivative is negative means slope is negative. Derivative is positive means slope is positive. And so That's the idea. Slope is positive when we're going up, slope is negative when we're going down. So this is the most important thing for you to remember, but now we need to understand how we're going to apply that and how we're going to use it. So let's go to the next page, and we'll look at some examples, or we'll look at some diagrams before we actually do a real problem. Okay, you see that we've got three rough sketches of graphs right here. And it's important to understand, for us to decide where a function is increasing or decreasing, we need more than just where is the derivative positive or where is the derivative negative. And what we have to understand is to get the whole interval for where a function is increasing or decreasing, we've actually got to know where it changes from increasing to decreasing or vice versa. So what I want you to notice in this is the first graph that I want you to look at. I've labeled points A and B, and of course those are x values. Now A, of course, corresponds to this position right up here, and B corresponds to the x value of the point that's right down here. And you see that at the value A, or at that point, or that high point, the function is changing from going to increasing. See, it's increasing here, and then it's decreasing when we get on the other side. So it's at this point where we change from increasing to decreasing. Now, whenever we change from increasing to decreasing is called, well, that's not quite right. I better hold off. What I want you to notice, though, of course, is on the left of A, if we look at tangent lines, the tangent lines have positive slopes. See, these tangent lines have positive slopes over here, okay? And if we look to the right of A, the tangent lines have negative slopes. Where that changes, that is, when we change from increasing to decreasing, is right up here at this point. And that tangent line is a horizontal line, and that tangent line has a slope of 0. Now, over here, remember, these slopes are positive, and the slopes where we're going down, these slopes are negative. That's kind of hard to read, isn't it? Negative. The slopes are negative. Now, when we get, remember, this is the value B right here. When we get to the value B for x, we change again from decreasing back to increasing. So here we're increasing, and the slopes of the tangent lines are once again positive. And this changing position, if we look at this position and we consider that tangent line, then that tangent line has a slope that's 0 because that's horizontal. Now here's what I'm wanting you to get out of that. When we're changing from positive to a negative slope, we go through a slope of 0 here. When we change from a negative, see, when we change from a negative to a positive slope, we went through a slope of 0, that peak. Now, these places where it can change is what we need to know, because we need to know the entire interval for which we're increasing or decreasing. So we need to know how far it goes before it changes from increasing to decreasing or vice versa. And so it's important to know where the slope is 0. See, it's important to know where that slope is 0 because that's a change position. Now, the x values where the slope is 0, those a's and b's are called critical numbers. That's where we change, or that's where we can change. Those are called critical numbers. Okay, that change happened at an A or a B, and that was where the derivative was 0, wasn't it? See, that was a place where f prime of x was 0. That meant a horizontal tangent line, didn't it? See, that's what that meant, because we have a slope of 0. I get so excited about this, I can't point to you. I can just draw, and you kind of see after the fact. Now, let's look at this second graph. In this case, is that the value A, again, that we change from increasing to decreasing. Actually, we're decreasing, and then we're increasing. And it's at this point where that change happens. Now, at that place, if you recall, there's not a slope. When x is A, the derivative is undefined. Remember a while back, that's one of the things that we learned, that the derivative is undefined at a pointed place on a graph. And we discussed that at the time for the reason, but at that position, there is not a tangent line. There's not a derivative. It's undefined there. Now, that's another case that we call a critical number. A is the x value. A is a critical number. I'm going to come back and critical number. I'm sorry, critical number. Now, let's look at this graph. When we see, of course, at A, the function's not defined at all. Here's the x value of A right here. At A, actually, we have an asymptote, don't we? A vertical asymptote, and the function is not defined there at all. But notice that we're increasing on this side and we're decreasing on this side. Now, in this case, we don't really call A a critical number, but we kind of get away with it. A is a place where we can have a change. There's something important about A, and of course, f prime of x is also undefined at A because the function's undefined. It's undefined at A. Now, what I'm really getting to here, and this is what the diagrams are for. Critical numbers, okay, in general, are x values for which f prime of x is either 0 or f prime of x is undefined. Now, the significance there is that at these critical numbers is where we can have a change from the function increasing to decreasing or vice versa. So, first we need to know what a critical number is. And second, we need to recognize that the critical numbers are the only places for which the graph can change directions. That's really significant. So for that reason, if we can find the critical numbers, then we'll find the boundaries from where we're increasing or decreasing. The critical numbers have to be the boundaries. Now, so it's time for us to look at an example of how we actually apply this. So we'll start an example, a fresh example, so that we have room on the next page. The power